the areas of chemical physics, and today I'm going to run through a few undergraduate level chemistry and physics questions, or chemistry questions I mean. So here's the first one. So we have copper ions in an aqueous solution that react with NH3 according to this equation. Giving us our copper, NH3, 2 plus aqueous, and the K, so the equilibrium constant for this is 6.3 times 10 to the 10. And then it wants us to calculate the solubility in grams per liter of copper bromide. So our copper bromide is going to dissolve and give us copper plus bromine ion. And the KSP for this is 6.3 times 10 to the minus 9. And so it wants us to calculate the solubility for copper bromide, given this K of solubility, but in a 0.64 molar NH3 solution. All right, so first, so what's going to happen here, right, is the copper bromide is going to separate, and then the copper ions are going to react with NH3 to give us copper ammonia. So if we're so the best thing to do to start is just to sum these reactions to get our total reaction, so if we sum these two, just add them up and put all the reactants on the reactant side. So there's our reactants, and they're going to react to give us our products. I'm going to just do it this way, and I should have put the aqueous in here. And plus copper ammonia. And now we can cancel anything that's on both sides, so we're going to get rid of the copper. And so our total reaction is just this. Okay, so now, awesome. So now we're going to want to get the K constant for this reaction, and so the K is just concentration of bromine, concentration of copper ammonia over our concentration of NH3 squared. Now if we look at our original reactions, this can be represented as the bromine, copper, copper plus times copper. Oops. I need to actually see the reactions. So we can represent it as our two reactions. So the first one I just wrote is actually the KSP, and then so that here would be our KSP, and this here would be our KF that we're given. Right, so if we multiply these two together, where this is now our KF, those coppers would cancel and we'd get exactly our K, right? So that means that the K for a reaction in our summed reaction is just the product of our two Ks. So 6.3 times 10 to the minus 9 times 6.3 times 10 to the 10, which gives us 396.9. Okay, so now we have the K for our reaction. I'm just going to erase some of this stuff. So we have the K for our summed reaction, so now we can use that to find our equilibrium concentrations. I'm just going to rewrite our total reaction just so that I remember it also. So copper bromide solid plus 2NH3 aqueous goes to bromine aqueous plus copper ammonia. There's two of those and it was plus. Okay, so we're starting. Now, with our K constant, we can figure out our equilibrium concentrations given our initial concentrations. So this is solid, so we don't need to worry about it. This guy is in a 0.64 molar amount, and we're assuming at the beginning that these are all 0. Now that's our initial, our change. Representing our change just by x. So if we reduce this by minus 2x, I'm going to say, because there's for every 2 moles of ammonia, we convert to 1 of each of these. So our change is minus 2x, and we're gaining x here and here. And so that equilibrium, we're going to have 0.64 molar minus 2x, x, and x. And now from our K constant, which is concentration of bromine, concentration of copper ammonia, over our concentration of NH3 squared, we can fill in our equilibrium values. So that would be x, x, and I'm just going to drop the molar here for ease of reading, squared. Okay, so that's what our K equals. All right, and so we have 369.9 is equal to x squared over 0.64 minus 2x all squared. Now I forgot, or I made a slight mistake here, so I'm just going to rectify that by just doing a bit of this math on hand. So let's just do that. So 369.9 square root. So if we take the square root of both sides, because they're squared on top and bottom, then we have 19.233 is equal to x over 0.64 minus 2x. We can pull the denominator up. So that'll be times 0.64 times 0.64. And so we're going to end up with 12.309 minus 38.466x equals x. So just bringing that up. Or 12.309 is equal to, so bringing this 38 over, 39.466x, or x is equal to this value divided by 39.466, which is 0.312. Okay, so that means our concentrations are 0.132, and now I'm just going to reappend the unit molar. Okay, so that's our concentration X. So now looking at the equation we've got, so that X is the concentration of our bromine, our copper ammonia, and our ammonia is some factor that depends on X, but that X is the concentration of both of these. So we're looking for our solubility. And now if we scroll up a little bit more, our solubility is going to be defined as the amount of moles of copper bromide that go into solution, but there's a 1-to-1 relationship with the bromine ion. So that means that however many moles of bromine we have in the end is the amount of moles of copper bromide that go into solution. So that means, looking at our equilibrium expression, that X is exactly equal to the amount of bromine, and so that X is also equal to the molar amount of our copper bromide. Okay, so that is our amount, but this is in moles per liter. We want it in grams per liter, so we need our molar mass of copper bromide, which is equal to M copper, the molar mass for copper, plus that for bromine, which is 63.546 plus 79.904. And so that's 143.45. And so our solubility in grams per liter is just 0.312 moles per liter times 143.45 grams per mole. And I should have realized that I also don't have this value, so I'm just going to do this again. 312 times 143.45. So our solubility in grams per liter is 44.76 grams per liter. Or, well, we have 0.64 molar NH3, so that would be our significant figures. So I would say about 45 grams per liter. Okay, so going through the solution here, so when copper bromide is added to solution. So we're going to sum the reactions. Our K is going to be product. We set up this ice table, which I showed as well. And we can equate to get a molar amount of our bromine of about 0.31. So that's pretty much exactly. 143.45. So I guess it's just that extra 2 there that gave mine a little bit of a nudge, but still it's about 44 point. That's curious, but anyway, about 45 grams per liter. So it looks like the solution's correct. There might have been a calculator error, but to me it looks like it's correct. I mean, it's about the same anyway. All right, so that looks good. So for this one, it's just asking what is the equilibrium constant for the following reaction in terms of the concentrations of each of the species. So this is just more of a general equation. So we have some solid plus some liquid going to our aqueous constituents, and actually I'm just going to, I don't need to do that in retrospect, I'm just going to scoot this down to our aqueous constituents. Alright, so recall that our K is our products over our reactants, where each of the product concentrations are raised to their appropriate powers. And each of the reactants will be as well. The only thing to know is any solids or liquids won't be included in our K constant because their concentration doesn't really change. They're basically in excess in the reaction. So we're only really considering the aqueous parts. Okay, so our K constant is going to be the concentration of our products. So it would be the concentration of C with the appropriate stoichiometric coefficient as a power. Concentration of D to the power of 1, so we don't need to include it. And then we can divide by the reactants, but you see that the reactants here are solid and liquid, so those are not included. And that means that that is our K constant. Okay, so now checking through the solution here. So yeah, so we're just going to raise each of the species to their appropriate coefficient. We don't include solid or liquids, and so we get C squared D. So that looks good. Solution is correct. Okay. All right, so here we have a Henry's law constant for the solubility of helium gas. Henry's law is just, or I guess I'll just go through the questions. So this is my third one. So we have a Henry's law constant, which I'm going to call KH, is 3.8 times 10 to the minus 4 molar per atmosphere. And it wants the value in terms of millimeters of mercury. So to do that, we just need that 1 atmosphere is 760 millimeters of mercury, or 760 torr. So then our KH is 3.8 times 10 to the minus 4 molar per atmosphere times 1 atmosphere per 760 millimeters of mercury. So the atmospheres cancel. And we now are just dividing 3.8 times 10 to the minus 4 by 760, which comes out to be 5.0 times 10 to the minus 7 molar per millimeters of mercury. Okay, so now the second part of the question just asks to calculate the concentration. So Henry's law relates the concentration of dissolved species to the Henry's law concentration, or Henry's law constant, and the partial pressure of the gas. And so part B says if our partial pressure is 293 millimeters mercury, what is the concentration of dissolved species? So for this, we just need to simply go through this equation. So our concentration will be 5.0 times 10 to the minus 7 molar per millimeters mercury, multiplied by the partial pressure, which comes out to be 1.465 times 10 to the minus 4 molar. Okay, and then part C asks what volume, what gas volume of helium is dissolved in 10 liters of water at this temperature and this partial pressure. So this is our molar amount, and recall that this is moles per liter. So if we have 10 liters of water, then we have the number of moles of helium is 1.465 times 10 to the minus 4 molar times 10 liters, or 1.465 times 10 to the minus 3 moles. Forgot here that I probably, well, that's a constant, so I think that's probably okay for significant figures, probably 1.47. Okay, so there's our number of moles of helium which are dissolved in our 10 liters of water. So now to get our volume of gas, we need to use the ideal gas law, so PV equals nRT. Solving for volume here, so volume is just nRT over P. And P in this case will just be our partial pressure. So N is this number of moles. R is our universal gas constant, which is 8.314 kilopascal liters per mole Kelvin. So that's the value that I always remember. So we're going to have to multiply this by our conversion to millimeters mercury, which is 760 per 101.325 kPa. So the kPa will cancel, and we'll actually get an R of 62.36 millimeters mercury liters per mole Kelvin. Our temperature is given in the question as 25 degrees Celsius, which we're going to have to convert again, so that's 273.15 plus 25 Kelvin, which equals 298.15 Kelvin. So there's our temperature, our R, we have our N, and we're given in the question that our pressure is 293 millimeters mercury. So now combining all this into our volume expression, we have that volume is 1.465 times 10 to the minus 3 moles times our gas constant, which is 62.36 millimeters mercury liters over mole Kelvin, times our temperature, which is 298.15 Kelvin, and divided by our pressure, which is 293 millimeters mercury. And we can quickly do a check on our units to make sure we didn't make any mistakes. And everything cancels, giving us liters, which is a volume, so that's good. And if we run this all through on our calculator, we get 0.09296 liters, which equals 92.96 milliliters. I rounded to 4 significant figures, but I don't know why. Because I believe in the question, I guess it gets tricky. Yeah. Okay, so that's our volume of helium gas, which is dissolved in 10 liters of water at that temperature and with that partial pressure. Okay, so let's go through the solutions. So first of all, might as well go up to the top here. So yeah, so we get about 5 times 10 to the minus 7, so that looks good. Our concentration is just by running through that, so 1.47 times 10 to the minus 4, so that looks good. And then running through this, we're going to use ideal gas. Which is about, which gives us 0.0933 liters, or about 93 mils. So it looks good. That would be just a different, and in rounding there, so solution is correct. Okay, so now we're going to consider a mixture. Consider a mixture of potassium chloride and potassium nitrate. And it's 43.2% potassium by mass. So what is our percent KCl by mass? So to start off, I'm just going to list our molar masses here. So that's our potassium, that's our chlorine, that is our nitrogen, and there should be more than one zero in there, and that is this is our oxygen. All right, so the molar mass of KCl is Mk plus MCl, which comes out to be 74.5513. And the molar mass for potassium nitrate is our potassium plus our nitrogen plus 3 times our oxygen. which comes out to be 101.1032. Okay, so the easiest way to start this off is just to assume we have 100 grams of sample. We can use any amount because we're dealing with fractions in the end anyway, and so it'll always be able to extend to any amount of mass, but 100 grams will make everything kind of nice. So if our M total is 100 grams, then that means that our mass of potassium is 43.2% of that, or 0.432 times 100 grams, which is equal to 43.2 grams. That means that the moles of potassium are 43.2 grams over the molar mass of potassium. Which is equal to 1.10491 moles, keeping an absurd amount of digits there. Okay, so if we have, if we consider A moles of KCl, that means that, and remember that this is a 1-to-1, so we get A moles of K from A moles of KCl. And maybe I'll just use a capital A just to differentiate a bit. So if we have A moles of KCl, then that means, and if we assume we have B moles of KNO3, and again, we have a 1-to-1 mixture, that means that A plus B must equal 1.10491, or B must equal 1.10491 moles minus A. Okay? And so if those are our molar amounts, and returning to, and now looking at our total expression, right? So if we have A moles of KCl, if we have A moles of KCl, then that means that A times our molar mass of KCl plus B times our molar mass of KNO3 is equal to our total mass, which in this case we're taking as 100 grams. But again, we're going to convert that anyway. Or from this expression above, A times our molar mass for KCl plus 1.10491 moles minus A times the molar mass of KNO3 is equal to 100 grams. Okay. So now collecting terms, we can calculate A because we know all of our molar masses. And so we'd have A, molar mass KCl minus molar mass KNO3 is equal to 100 grams minus 1.10491 times our molar mass for KNO3. And actually, I'm just going to stick that in there. So that's moles. So a quick unit check before we go too far, right? So this is going to be, A is going to be in moles. So the whole thing on the right should be in moles. This is grams per mole times moles, so that's going to be in grams. So this side's going to be in grams. but that's in grams per mole. So when we divide it, we should get moles out the other side. So that looks pretty good. Putting in values here now. So this is A, 74.55. I'm just going to start cutting these down a bit. So rather than keeping all those units, 101.10. And this is 1.105 times 101.10. And that's in moles. All right, so the moles here will cancel, leaving grams. And so, and then this here is going to be A times minus 26.55 is equal to, and on this side, if we do that through, is minus 11.71. And that's in grams per mole. And so our A, doing that division, comes out to be 0.44102 moles. So I just expanded the units, the digits back out again, and the amount of significant digits, I guess, would be 3. So more like 0.441 moles. Okay. So now, if that's our molar amount, that's our molar amount of A, which is the molar amount of KCl. So that means our mass of KCl is just our molar mass, so 74.5513 grams per mole, times our number of moles, which is 0.44102. Again, just keeping all the digits while I do the calculation and then doing the rounding after, which equals 32.879 grams, or about 32.9 grams. So there's our mass amount in our 100-gram sample. So again, that we're just assuming that 100 grams, but that's fine because we're looking for a percentage, right? So our percent KCl is just this mass amount, 32.879 over our full, which is 100 grams, which is, and then multiplied by 100%, which is 32.9%, rounded to our 3 significant digits. Okay, so that's our mass percent of KCl. So that's our final answer. Okay, looking through the solution, the easiest way is to assume that the mass is 100 grams and then use that to find our percentage. Again, this will apply to any mass amount, not just the 100 grams, but a 100 gram sample makes it easier. So we can calculate our mass of potassium, our moles of potassium. Let's also assume that the mass of chlorine is Y. Okay, so then they've added in a few extra steps. Okay. Moles of nitrate. So I don't think that's necessary, but it's doable. It's probably just cyclical, if I were to guess, as long as they don't make any mistakes. So they've calculated the moles of chlorine. and use that to calculate the number of moles, but it comes out to be 0.44037, so roughly the same. My guess would be just some calculator error somewhere in here, or just some rounding error. Rounding error is what I meant, probably not a calculator error. But then using this, we get 32.83 grams, and in the end 32.83%. So whereas mine would be rounded to 2 decimals would be 0.88. So likely it's just off by some rounding differences. I would say it's probably correct, or I'd say the solution is correct. They just went a slightly different path by calculating the other constituents as well, but I don't think that was necessary. But yeah. Okay, so for my fifth one here, it asks, is SCl2 polar or non-polar? So first off, so chlorine, we're going to start off by drawing our Lewis structure to get our structure. So chlorine would be like this, as it has 7 valence electrons. Sulfur is similar to oxygen. So it's got 2 lone pairs and two electrons for bonding, or 2 non-paired electrons, and so we're going to get bonds in here. So that all looks good. So now when we draw the actual structure, the bonds and the lone pairs are going to take up a tetrahedral structure, and so the actual structure will look something more similar to this. Where I'm using these wedges to show that they're coming out of the page. And it's going to want to keep the lone pairs on chlorine as far away from its own lone pairs. And so this lone pair is going to be going back into the page. And so the whole structure is the entire structure is tetrahedral, including the lone pairs, but the molecular geometry is just including the atoms, not the lone pairs. So this would be bent, but it's always a tetrahedral type structure with a full octet, but you don't include the lone pairs in the molecular structure. The sulfur chlorine bond is going to be polar. So each of these will be polar towards the chlorines, and so the net dipole will be somewhere in between. And so looking at the structure and knowing that you are going to get some dipole between dissimilar atoms, so sulfur and chlorine are not the same. And chlorine is more electronegative, so you're going to get some dipole from that, and so I would say it's polar. Okay, so polarity is defined as separation of charge. There's a mild dipole between chlorine and sulfur, and it's a bent structure. So there's no symmetry here, so the dipole is not going to cancel, and so we're going to get a dipole. So the solution is correct. And okay, so which of the following molecules may have hydrogen bonds? This is my 6th one. So I'm just going to start off by drawing some of the structures. So for CH3F, we've got carbon, hydrogen, 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 fluorine. So for a hydrogen bond, we need some electronegative atom bonded to hydrogen. So in this case, we don't have that. Also, if we draw CH3Br, it's going to be very similar. Right, so we don't have some electronegative atom bonded to hydrogen in either of these cases, so neither of these two are going to allow for hydrogen bonding. If we draw CH3NH2, then it would be something along these lines. And so we do have an electronegative atom bonded to hydrogen, and so it's possible we could get some hydrogen bonding here. And so there might be some small hydrogen bonding. The only reason I say small is because this other hydrogen here is going to be in the way, but it should be possible. And then if we get to the final one, we have our OH, and this definitely will have hydrogen bonding, as now we have an open, it's now open for accepting of the oxygen side, and the hydrogen will readily donate a hydrogen bond. So this one for sure, whereas this one should be able to with the more electronegative atom bonded to H, although it should be also a little bit hindered because of the two hydrogen atoms. Okay, so remember that when you want a hydrogen bond, a hydrogen atom must be bonded to an electronegative atom, such as oxygen, nitrogen, or fluorine. So CH3F, no, because it's not bonded to any hydrogens. And then, so the only possibilities are these two. And so theoretically they should both allow it, although CH3OH definitely will have hydrogen bonding. So I'll say the solution is correct. Okay, so it wants us to rank these elements according to their first ionization energy. And I'm just going to write them down this way. And I'm going to write out their valence configurations. So gallium's valence is 4s2, well, I guess not valence, but highest orbital electron configuration. And these just go down, or not down, but across the periodic table. And so what largely affects your first ionization energy is how much energy it takes to remove these electrons, and also how stable the cation is. But the largest thing is really how difficult it is to remove an electron. And so the biggest thing that leads to that is actually your nucleus, because your nucleus is heavily positively charged, and as you go right across the periodic table, we're increasing this charge, which means that as we go right across the periodic table, these electrons are actually more and more tightly held. The only thing that alters this is we get a little bit of stabilization for half-filled orbitals. So the only case this comes in is arsenic, and for filled orbitals, which is krypton. But of course, kryptons are a noble gas, so it's on the far right of the periodic table, so it still kind of follows that trend. So with this idea that it's going to increase across from the right, then we can see that potassium is going to be our lowest, krypton is going to be our highest, and then it should just increase down from there, with arsenic and selenium swapping places because arsenic has a bit of stabilization due to the orbital being half filled. So to answer the question here, then for our first ionization energy, it should be potassium smallest, which is less than gallium, which is less than germanium, which is less than, and now arsenic and selenium are going to swap, so less than selenium, which is less than arsenic, which is less than bromine, which is less than krypton. Okay, so basically it goes right across the periodic table from left to right, except selenium and arsenic are swapped. Okay, so the solution here goes through a bit of what I discussed. So they're going actually from highest to lowest here, but krypton, bromine, arsenic, selenium, germanium, calcium? Calcium wasn't in there. Gallium, and then potassium. And also I don't think calcium would be in between there, so that's just a mistake. But yeah, so it just basically goes left to right across the periodic table with some swaps in places where you get half-filled shells. So the solution is correct. Okay, so what is the general formula for a combustion reaction? So in combustion, at least with hydrocarbons, I should say, we're going to add oxygen and evolve CO2 and water. And then we need to balance. So just for an example of this, if we want to know what happens when we burn C6H12, then we would add oxygen and yield CO2 plus water. And so to balance it, all we need to do is just look at our carbon and hydrogens. So we need 6 of these. We need 6 of these. And then we've got 12 plus 18 oxygens. So we need 9 of these. And then there's our balanced combustion for C6H12. So just to reiterate, In general, whenever you have a combustion, you add oxygen and your products are carbon dioxide and water. And so whatever you burn, you just add these and balance. Okay, so includes carbon dioxide and water, and it's often exothermic. All right, so this solution looks correct to me. Okay. How long is this going to take? Not too long. Okay. So we have a 0.423 impure sodium nitrate sample, and we've converted all the sodium nitrate to 0.286 for sodium nitrite and oxygen gas. So it wants us to determine the percent of sodium nitrate in the original sample. So first off, we might as well do all our molar masses. So sodium is 22.989769 grams per mole. N is 14.0067. Oxygen is 15.9994. And so our molar mass for sodium nitrite, which is NaNO2, is just the molar mass for sodium plus that for nitrogen plus 2 times that for oxygen, which comes out to be 68.995269 grams per mole. And so if we have, we want to know the mass percentage now of sodium that takes up that 0.2864 of sodium nitrite. So we can get a mass percentage by just dividing the sodium molar mass by the sodium nitrite mass. So that's 22.989769 grams per mole divided by 68.995269, which is 0.3332079. Okay, so that means that fraction of our sodium nitrate mass is sodium. So our mass of sodium is this fraction multiplied by our total, which is 0.2864 grams. So that equals 0.09543. So that's our mass of sodium in the sample. Now, if we've converted sodium nitrate to sodium nitrite, the sodium mass hasn't changed, meaning that's also the mass of sodium in our sodium nitrate. So to start off, our mass of sodium nitrate, our molar mass for sodium nitrate is just the molar mass for sodium, plus that for nitrogen, plus 3 times that for oxygen, which if we plug in the numbers, comes out to be 84.994664 grams per mole. Okay, and now to convert our mass of sodium to a mass of sodium nitrate, we just need our mass percentage. So our mass of sodium nitrate is just our mass of sodium. I'll do it this way first. It's just our mass of sodium multiplied by our molar mass of sodium nitrate over our molar mass of sodium. Or 1 over, that's 1 over our mass fraction for sodium. Or that's the mass fraction for sodium nitrate relative to sodium. And so then that's 0.09543 grams times our 84.994664 grams per mole over 22.989769, which equals 0.35281 grams. So that's our mass of sodium nitrate. And so it wants a mass fraction. So our mass of sodium nitrate over our mass total times 100%. 0.35281 grams over 0.4230 grams, which is equal to times 100%, which is equal to 83.41%. And so then that's our percentage fraction of sodium nitrate of the impure sample. Okay, so looking at the solution here, we're going to start with our molar masses. We can convert sodium nitrite into sodium nitrate by using some of these mass fractions, which is basically what I did. But I separated it out a little bit more. To give us, oh, right, I guess, yeah, we could have just straight up converted the mass of sodium nitrite to nitrite without going through the sodium mass, but oh well. And we get a percent mass of 83.4, so it looks like that all comes out to be the same. So the solution is correct. Okay, and I'm actually going to say that that's good for this stream. So I hope everyone enjoyed going through these questions. If you did, please subscribe to OneClass. If you want to leave questions, please follow the links below the video. This has been Jeff Krause for OneClass, and I hope to